Who could have predicted such a catastrophe? How could such a prosperous world be plunged into darkness in an instant? 66 million years ago, an ominous shadow hung over the Earth. The once invincible dinosaurs were the first victims of this cataclysm. Unable to adapt to this hostile new world, they disappeared forever, leaving behind a deafening silence. But this extinction was only the beginning of an unprecedented upheaval. For in the rubble of this lost world, a new era would be born, shaped by the survivors of this apocalypse. An era in which nothing would ever be the same again. Dear traveler, welcome. Today we're going back in time to discover the mysteries surrounding the world after the extinction of the dinosaurs. What really happened after the last roar of the T-Rex faded into the echoes of time? But before you set off on your next adventure, make sure you like the video and subscribe to the channel so you don't miss a thing. Thanks, and have a great trip! "66 million years ago, the Earth experienced one of the greatest catastrophes in its history, the Cretaceous-Paleocene extinction. To understand what might have caused such destruction, we need to analyze every fossil record from this dark period. But before we delve into this enigma, let's take a look at what our planet Earth and its inhabitants looked like up until then. At the end of the Cretaceous, just before this fifth and final mass extinction, the Earth was a world of contrasts and flourishing diversity. The continents, though still in motion, had by then almost found their present position, Pangaea, that original supercontinent, having fragmented long before. Australia was still attached to Antarctica, while North America and the European continent were still linked to Greenland, but had not yet begun to separate. Under the effect of plate tectonics, India, which formed a large continent in its own right, was still moving. After breaking away from Madagascar, it was about to collide with Asia. The Tethys Sea kept the African continent at a great distance from present-day Europe, which was nevertheless joined together by two continental bridges that would later give rise to Spain and Italy. The Cretaceous period is renowned for its particularly high average sea level, reaching a peak 250 meters higher than today. With such a level, important coastal areas would be underwater today, but not only. At that time, Europe was completely submerged, forming an archipelago. While the face of our planet was largely recognizable at this stage of its evolution, climatic conditions were very different. In correlation with sea levels, we note the absence of ice at the poles. But above all, the climate was temperate, even hot and humid, with average temperatures above 18 degrees Celsius or 64 degrees Fahrenheit, compared with 15 degrees Celsius or 59 degrees Fahrenheit today, which explains the incredible abundance of life, both on land and in aquatic environments. During this period, considered to be one of the hottest in the planet's history, the fauna was dominated by dinosaurs, the titans that reigned unchallenged on dry land. Gigantic herbivores like the Triceratops, easily recognized by its crest and horns, roamed the plains of Laurasia, grazing without respite. Fierce predators such as Tyrannosaurus rex, one of the most feared carnivores, hunted their prey in the dense green forests of Asia and North America. Mammals were less imposing than dinosaurs, but were relatively present, albeit more discreet, and populated every continent. Flying reptiles of the pterosaur family dominated the skies. The huge shadows of these giants on the ground signaled their presence in the air. Notably, the Quetzalcoatlus, which could reach 15 meters or 50 feet wingspan. The oceans teemed with life, frequented by countless creatures, including the Mosasaurus. The largest specimens of this giant marine lizard could measure up to 15 meters or 50 feet in length. It's easy to imagine that it must have been particularly feared by other species living in marshy areas. Vegetation was equally abundant and varied. The previously abundant conifers, ferns, and cycads soon lost ground to flowering plants of the angiosperm family. The proliferation of these new plants provided a rich source of food for a multitude of insects, small mammals, and reptiles. In the form of herbaceous plants, shrubs, and lianas, among others, they were at the origin of a complex interconnected ecosystem. As angiosperms slowly conquered the land, they attracted pollinating insects, which in turn became the prey of small feathered dinosaurs and other modest-sized mammals. Large herbivores with their powerful jaws sculpted vegetation, while carnivores regulated populations. But this world, where life abounded in all its forms, was about to undergo a cataclysmic change. Without the slightest warning, our planet, accustomed to sustained volcanic activity, experienced an unprecedented period of darkness. Imagine this dynamic, colorful universe suddenly plunged into total darkness. The sun's rays, veiled by clouds of dust and ash, can no longer reach our planet's inner atmosphere. Day no longer dawns. The darkness lasts for months, even years. Our Earth experiences the longest night of its existence. The only sound left is one of despair. That of the piercing cries of animals seized by a primordial terror, then witnesses of this planetary disaster, tearing their universe apart. The cause? The planet's volcanic activity is certainly responsible for many of the setbacks. It may even have contributed significantly, through a few intense eruptions, to the disappearance of life on the globe. Enormous quantities of gases released into the atmosphere would have caused severe climate instability. Abundantly charged with sulfur and other minerals, this protective atmosphere would have blocked the sun's rays, greatly disrupting flora and fauna, as well as the carbon cycle. In fact, during the same period, a major volcanic episode disrupted the Deccan, a province in western India, as witnessed by countless fossilized remains. But the fatal blow came from the impact of a gigantic asteroid, whose crater, still visible today, is located on Mexico's Yucatan Peninsula. The virulence of this unfortunate collision was comparable to that of 10 billion atomic bombs. The crash of this celestial object, whose size is estimated at between 10 kilometers or 6 miles and 80 kilometers or 50 miles in diameter, and its speed at 20 kilometers per second, caused a succession of disastrous consequences. Living creatures for hundreds of kilometers around the impact zone perished instantly under the force of the impact. The power of the impact set vegetation ablaze for thousands of kilometers. A devastating tsunami, reaching a height of 1,500 meters or 5,000 feet, then swept violently across the landscape before a volcanic winter enveloped the entire Earth. Fatally, a drastic drop in temperatures followed. In this nameless chaos, the surviving dinosaurs tried to fight for survival. Majestic creatures like Triceratops and Tyrannosaurus rex, which had dominated terrestrial ecosystems for millions of years, found themselves confronted with an environment that was suddenly transformed into a most hostile world. In the absence of a suitable environment, non-carbonized plants withered, food chains collapsed, and with them, the last non-avian dinosaur species. Ultimately, this major event led to the extinction of around 75% of all life on the planet. Between 6 and 8 species out of 10 became extinct in both the plant and animal kingdoms. Today, only fossils bear witness to their real existence, some of them giving us clues as to their last moments on Earth. Nevertheless, in the shadow of this mass extinction, life has found a way to persevere. If the titans of yesteryear, particularly exposed to events, didn't have time to adapt, against all odds, other creatures survived, far less imposing. Most of the mammals lucky enough to escape this brutal and terrible event were able to shelter underground or exploit new ecological niches. But not all dinosaurs disappeared. Birds managed to survive the ordeal. According to scientists, the study of fossils dating from this sinister period indicates that animals whose mass was greater than 25 kilograms or 55 pounds did not survive, with the exception of certain particularly resistant turtles and crocodiles. As the dinosaurs disappeared, unsuspecting survivors laid the foundations of a new ecosystem. This massive extinction event closes a chapter in the history of our planet, that of the Mesozoic geological era, which spanned almost 185 million years. Then, 66 million years ago, our planet entered a new era, the Cenozoic, which saw the birth of life as we know it today. But before becoming the beautiful planet we know today, populated by countless species including humans, almost everything had to be reinvented. This renewal was marked by a first period, the Paleogene. It is the first of 3 periods making up the Cenozoic era, the other 2 being the Neogene and the Quaternary, the very era in which we now find ourselves. The Paleogene period, which stretches from 66 to 23.03 million years ago, is subdivided into 3 distinct eras. The oldest, the Paleocene, lasts 10 million years. It corresponds to the period when the Earth began to recover from the mass extinction that closed the Cretaceous. The Eocene, the second and longest of the 3 epochs, was marked by a warm climate for 22 million years, favoring rapid diversification of life and the expansion of mammals and flowering plants. The third Paleogene epoch, the Oligocene, extends from 33.9 to 23.03 million years ago and corresponds to a period of slow global cooling. Once again, animals and plants had to demonstrate a major capacity for adaptation. But let's return to the moment when the Earth was the scene of the 5th biological crisis, the one that claimed the lives of the great reptiles, including the dinosaurs and pterosaurs, and definitively wiped out various families of mollusks, notably the ammonites. Following the destructive impact of the meteorite in the Gulf of Mexico and the lava flows flooding the Deccan Plateau in India, a volcanic winter set in. The fire and brimstone planet is rapidly turning into a dark, cold land, its atmosphere saturated with ash and sulfur. According to a 2017 study, however, the low temperatures did not persist for more than 10 years. Unfortunately, this period, although extremely short on the geological timescale, is more than enough to harm all living beings, especially non-marine species. Animals and plants, if they did not perish in the gigantic fires, are now freezing to death. Large herbivores with nothing left to eat are disappearing one by one. Famine spreads far beyond the impact site or volcanic region. Carnivores, even if they managed to survive for a while, succumbed in their turn. The cruel lack of light hinders photosynthesis. In the oceans, phytoplankton are also dying. The food chain is wiped out. Only small rodents, insects, reptiles, and birds can survive. In the end, apart from insects and the vast majority of mollusks, which managed to continue their evolution, it was the animal species belonging to the 4 orders of reptiles that escaped this hecatomb. Turtles, snakes, lizards, and crocodiles came out on top, proving extremely resilient during this chaotic planetary reshuffle. Indeed, less than a year after the Earth was shaken by this series of cataclysms, the skies are gradually clearing. Blue skies gradually pierce the harmful clouds, and the sun finally reappears. The seeds and pollen that have been preserved can at last begin a new germination process. Carried by the winds, these seeds, most of them fern seeds, are planted all over the planet, which is greening up here and there as best it can. This meager pittance, while good for insects, is not yet enough to allow larger animal species to thrive. It would take another decade for other plant species to develop, namely palm trees. Once the chaos had dissipated, the Earth regained a certain equilibrium during the first geological period of the Cenozoic era. This period, the Paleocene, extends from 56 to 66 million years ago on the stratigraphic scale. It is divided into 3 stages: the Danian, the oldest, which lasts almost 5 million years, the Selandian, which lasts just over 2 million years, and the Thanatian, which spans just over 3 million years. Following the Cretaceous period, the Paleocene ushered in an era of biological recovery and renewal. After the brief, macabre volcanic winter, the climate gradually became milder. While the Earth's overall temperature was generally lower than in the previous era, it was still higher than today. As you can well imagine, this global warmth allowed lush biodiversity to flourish. Dense forests quickly developed, populated by diverse flora and fauna. On the other hand, the climate was characterized by increased humidity. This increased humidity translated into abundant precipitation, evenly distributed throughout the year. As a result, North America saw the emergence of even more opulent forests than in the previous period, while mangroves flourished in Australia, then positioned at southern latitudes around 65 degrees. Redwoods colonized all continents, which were gradually being covered by primary forests. At the same time, cacti were making their appearance. Tropical forests spread on both sides of the equator up to 50 degrees latitude, well beyond their current limits. A subtropical climate prevailed over areas that today are temperate, even polar. In fact, traces of fossilized flora have been found in Alaska, proving that these regions did not enjoy an icy climate, but rather a cool, temperate one. They were then covered with forests of broad-leaved deciduous trees. Flowering plants, or angiosperms, continued their conquest of land, with the precious help of numerous pollinating insects. At the same time, the continents continued the slow drift that had begun with the fragmentation of the supercontinent Pangaea. This geological transformation is characterized by three major movements. Greenland and North America began to drift apart, and India and Asia began to collide, leading to the formation of the Himalayas. Finally, Australia begins to break its link with Antarctica. As for the other continents, their separation is already significant, and they continue to move further and further apart. This same period saw the inland seas of North America and Europe partially recede. The newly emerged land, rich in sediment, offered new spaces for fauna and flora that were eager to proliferate. Mammals in particular flourished during this period to an unprecedented degree. Unlike the previous period, they no longer had to make do with the few crumbs left by the dinosaurs, which had not survived. They were thus able to take advantage of ecological niches that were finally accessible, to the extent that 22 new orders were born over the 10 million years covered by the Paleocene. Among these emerging mammals was Ptelotis, a small rodent that, like our squirrels, could climb trees. It left many traces of its existence during this period, notably in Canada. Fossils of another small mammal have also been discovered in the USA and Canada. These belong to the Purgatorius, an animal the size of a rat or squirrel. Equipped with particularly mobile ankles, this small mammal was probably omnivorous, being as agile in trees as on the ground. It probably fed on fruit and insects, but also, like all scavengers, on all kinds of animal remains, even stolen eggs. There's every reason to believe that its growth cycle and mode of reproduction were similar to those of our contemporary rodents. In other words, rapid growth with a short lifespan, and consequently, early sexual maturity. But above all, Purgatorius stands out as an emblematic species of the Paleocene, embodying one of the first known links in the evolutionary line of primates, our distant ancestors. Marsupials resembling our opossums have been found in South America and Australia, the latter having probably migrated via Antarctica before the land separation. Criacus, another agile raccoon-like climber, measuring 1 meter from snout to tail tip, has also colonized the forest. Doubtless omnivorous, its diet includes insects, fruit, eggs, and small mammals. A member of the same family, the Arctocyan was also found in Europe. This bear dog was a type of mammal that, although extinct today, has left an indelible imprint on the fossil record. About the size of a large dog, its short, powerful legs had claw-like nails at the tips. Although it moved like a bear, or even a human, on the soles of its feet, its robust legs suggested an ability to cover vast territories in search of food. Its elongated, solid skull featured a pronounced sagittal crest, the hallmark of a powerful masticatory musculature. Moreover, its dental characteristics indicate that it was probably an ancestor of our modern bears, then in transition from a carnivorous to a herbivorous diet. In fact, the fossils studied revealed robust molars for crushing, incisors adapted to plucking leaves, and tapered canines resembling tusks. The Arctocyon, Primates, the most widespread species in Europe from this period, suggests an animal with little specialization. This is probably why it proved particularly adaptable to a variety of environments and food sources. A valuable link between past and present, this bear dog continues to captivate scientists with its remarkable adaptability. Creodonts also made their appearance during the Paleocene. These carnivorous mammals are close neighbors of our felines, with whom they share a common ancestor. A precursor of the primate order, the Plesiadapis, was also present at this time, particularly in North America and Europe. Resembling a squirrel or a lemur with sharp claws, its habitat was the forest, and its favorite food was insects. Over time, various hoofed species have similarly emerged, considered the ancestors of our horses, pigs, and rhinoceroses. Of modest build, these new arrivals were no bigger than sheep, with the exception of the Ankylodon Saurognathus, whose size was similar to that of a bear. This carnivorous mammal, with its powerful jaws and well-developed canine teeth, was the largest mesonychid known at the time and reigned mainly in North America. Its sharp teeth and exceptionally strong jaw muscles would have enabled it to tear flesh with formidable efficiency, making it a terrible predator. While life returned to normal during the Paleocene, with many new species appearing on Earth, the sky was populated solely by clouds. Pteranodontidae, the flying vertebrates of the pterosaur family, like many other species, did not survive the previous extinction due to a lack of tree vegetation. The two main bird types present at the beginning of the Paleocene, the only surviving dinosaurs, were neorniths, a subclass of modern birds. Divided into two clades, the paleognaths and the neognaths, these vertebrates were rather large, but above all flightless. Among the neognaths, present in greater numbers during this period, the diatrema, which could reach 2 meters in height, hunted its prey in frenzied chases. Indeed, although these birds were unable to fly, they were very good runners, much to the chagrin of their victims, who were quickly devoured. Another imposing silhouette stood out in the lush forests and marshy plains of North America and Europe, particularly France. The Gastornis, a winged titan, standing 2 meters tall, dominated the lands of the Old World. Its short wings and sturdy legs testify to its predisposition to tread the ground rather than the skies. Its massive beak suggests a remarkable grasping power, capable of crushing its meals with ease. By the way, was the Gastornis a carnivore or a herbivore? Had it too inherited the ferocious appetite of the famous terror birds that plagued other dinosaurs? Despite the enormous size of its beak, this gigantic chicken, just as frightening as it looked, actually ate nothing but plants. As for the paleognaths, they are distinguished from the other clade by their skeletal structure, which is singularly devoid of the brevis, the sternal bone to which the powerful wing muscles are attached. Their contemporary representatives are the ratites, which include ostriches, emus, and kiwis. Their reduced wings, non-functional for flight, and heavy body structure suggest that these land birds must have been omnivorous or herbivorous. All these varieties of land animals, along with a wide range of insects, played an important role in Paleocene handful of thousands of years. As if the planet's thermostat had locked into a warming position, global temperatures soared. This phenomenon, which marks the end of the Paleocene, occurred around 56 million years ago. This transition between two geological eras, which in turn reshaped a number of ecosystems, is known as the PETM, or Paleocene-Eocene thermal maximum. The PETM is characterized by a sudden rise in global temperature, estimated at between plus 8 degrees Celsius and plus 14 degrees Fahrenheit. This hyperthermal episode, which occurred in the blink of an eye on the scale of geological time, was accompanied by massive releases of carbon into the atmosphere. According to experts, 2,000 gigatons of methane may have been released into the atmosphere during this global warming. This greenhouse gas, considered to be 10 times more potent than carbon dioxide, will have contributed significantly to the rise in global temperature. But what process could have led to this tipping point being crossed, resulting in climate change with major biological consequences? For scientists, only two explanations seem plausible. The significant increase in atmospheric carbon levels could be the result of intense volcanic activity, or it could be attributed to the destabilization of methane hydrates on the ocean floor. Some even suggest that these two processes may have been successive, with the former generating the latter. The hydrothermal vents attributed to volcanoes would then have triggered the onset of warming. Then, through a positive feedback effect, as initial temperatures rose, they in turn destabilized immense carbon reservoirs, namely the submarine methane hydrates. The Earth's topography at the time could also have been a factor in this exceptional warming. The northern and southern parts of the American continent were not yet linked by the Isthmus of Panama, and the Mediterranean was still communicating with the Indian Ocean. As for Antarctica, it was still connected to South America, making thermal insulation impossible. This configuration explains why there were no ice caps covering the Earth at the beginning of this period. As proof of this, fossilized traces of Nothophagus, a southern beach still found today in Patagonia, have been found in Antarctica, then covered by so-called temperate forests. But not only. In 2012, researchers reported the discovery of fossils from a tropical forest in the same region. Pollens from ferns and palms were found, as well as fossils corresponding to crocodile species. It turns out that the North Pole was also home to tropical flora and fauna. In 2017, specialists revealed evidence of the existence of mangroves. However, while this warming benefits some species, notably vegetation, it affects others, particularly marine organisms, with calcareous shells. Foraminifera, the shell-bearing protozoan organisms that once populated the seabed, and which are particularly sensitive to the rising acidity of their environment, have been hit hard. It is estimated that 50% of them did not survive, as did many other marine species that also disappeared during this exceptional climatic event. Seasonal characteristics, such as more abundant rainfall, enabled tropical rainforests to cover even more territory. As new ecological niches opened up in these mutated regions, intercontinental migrations took place and modern mammal species emerged. Admittedly, the Paleocene extinction is smaller than the one that wiped out dinosaur populations. But this minor extinction, unlike the many others the Earth may have experienced, nonetheless marks a decisive turning point in the evolution of species. It led to the second Paleogene period, the Eocene, which extended from 56 to 34 million years ago. This period is made up of three subdivisions: the Upper Eocene, the Middle Eocene, and the Lower Eocene, the last two of which themselves comprise different stages. Succeeding the Paleocene, this new period was marked by the emergence of the first cetaceans and the first modern mammals. But above all, it marks the advent of the dominant era of the latter. From surviving prey alongside the dinosaurs, mammals became the main predators over time. At the beginning of the Eocene, the continent, still drifting, took on a shape even more recognizable to us, while ocean currents underwent fundamental changes. The Tethys Sea, which separated the African continent from Eurasia, shrank even further during this period, to the benefit of the Atlantic Ocean. The latter opened wider, pushing North America further away from Europe, as the continent continued its westward drift. After breaking away from Europe, a newly formed continent drifted northwards, giving rise to the Greenland we know today. This geological event, which took place 55 million years ago, led to violent volcanic eruptions between present-day Greenland and Great Britain. Huge quantities of methane and carbon dioxide were released into the atmosphere, contributing to a further rise in temperature and raising the surface temperature of Arctic zones by a further 6 degrees. As for the Pacific Ocean, which has never undergone major changes, it is already as deep as it is today. Meanwhile, India continues its collision with Asia. As a result of this spectacular rapprochement, the land underwent significant changes, giving rise to the famous Himalayas. Australia and Antarctica are now two distinct continents, gradually drifting apart. Australia heads north, while Antarctica, then lush and green, moves towards the South Pole. During the first half of the Eocene, the climate that dominated the planet was largely tropical, to the extent that the two poles, still devoid of the slightest ice, were covered with rich vegetation. Dense jungles and forests, dominated by palms and broad-leaved trees, cover most of the land up to high latitudes. Taking advantage of this warm, humid climate, the flora and fauna have undergone unprecedented diversification over several million years. Mammals in particular evolved rapidly, taking advantage of the niches left vacant by the last dinosaurs, now totally extinct. Birds also continued to develop, as did reptiles, which became much less dominant. While flying birds were less common during the Paleocene than large flightless birds like Gastornis, new species began to appear and diversify. The high skies of the Eocene, hitherto devoid of animal traces, began to welcome new bird species. One notable example is the Pelagornis sandersi, reputed to have been one of the largest flying birds in history. Its wingspan sometimes reaches over 7 meters, or 23 feet. Compared with our largest modern birds, such as the Andean condor, it appears to be at least twice as big. Pelagornis sandersi is a seabird that probably glided long distances over the oceans. Using air currents to maintain flight with minimum effort, it is a fascinating example of how birds adapted to life in the skies during the Eocene. In South America, Coleopterus, small predatory birds descended from two-legged dinosaurs, displayed similar behaviors to their ancestors. Nicknamed terror birds, if they were able to fly, they must have been very limited. Indeed, their small wings indicate that they spent most of their time on the ground. During this period, many new groups appeared, including around 50 million years ago, Pakicetus, the ancestor of the whale. This mammal represents a key stage in the evolutionary transition of cetaceans from land to the deep sea. Indeed, this precursor of the whale, which lived near the rivers and deltas of Pakistan, is not an aquatic animal, but a terrestrial one. While the study of its skull, and in particular the structure of its inner ear, leaves no doubt that it belonged to the cetacean group, Pakicetus had a unique anatomy. It had a streamlined body, robust limbs perfectly adapted to running, and a head adorned with a long pointed snout, containing teeth designed to tear flesh. These characteristics show that it was an agile, opportunistic predator with a carnivorous diet. Its particularly varied menu included small land animals and fish. Thanks to the study of fossils, scientists are now able to confirm that Pakicetus is an extinct genus of cetacean. Its ankles, identical to those of artiodactyls, underline its membership of the great ungulate family, which itself heralded the emergence of the first aquatic ancestors of whales. The Pakicetus alone embodies the extraordinary evolutionary journey of cetaceans. From its first steps on land to its conquest of the oceans, it opens a fascinating chapter in natural history. Over the millennia, the swampy area where the Pakicetus resides, the region of the globe where the Tethys Sea once stood, has seen many species acclimatized to this environment. Pakicetus itself, spending most of its time foraging in the water, as our crocodiles do, probably gave rise to Ambulocetus, in other words, the walking whale. Measuring up to 3 meters or 10 feet in length and weighing up to 300 kilograms or 660 pounds, it used to blend into the landscape, both terrestrial and aquatic, and wait for prey to come close enough. Lacking external ears, it was nevertheless perfectly able to pick up the vibrations emitted by its prey, whether in the water or on land. Although its hind legs made it more agile in the water, where it undulated like a whale, this carnivore, half aquatic, half terrestrial, also moved quite well on land. In this prosperous environment, other carnivorous aquatic mammals emerged alongside it, such as Himalayacetus and Indocetus, also early whales. On land, many newcomers also appeared during the Eocene. No bigger than a dog, Phenacotus was an ungulate of the placental mammal class. Modest in size and light in build, it was characterized by a digitigrade gait, similar to that of our tapirs. Its relatively predominant middle toe bore most of its body weight, while the other 4 toes on either side probably ended in hooves. In other words, Phenacotus heralded the tridactyl type common to perissodactyls, whose future families will almost certainly include equids such as horses, donkeys, and zebras. In fact, the first member of the evolutionary horse family appeared at the same time, Hyracotherium, also known as Eohippus. Often nicknamed the dawn horse, it is considered one of the oldest known ancestors of modern horses. It is therefore one of the herbivorous mammals that significantly marked the Paleogene period. This small ungulate, which lives in the forests of North America and Western Europe, is no bigger than the average dog, at around 30 centimeters or 12 inches high at the withers. This creature, though different in appearance from today's horses, played a key role in the evolution of these mammals and remains an important subject of study for paleontologists. Among the ungulate mammals of this family, Megacerops, a distant cousin of the rhinoceros, also made its debut towards the end of the Eocene, also in North America. It belongs to the first giant mammals of this period. With a build equivalent to that of an African forest elephant, it measured around 2.5 meters at the withers and could reach up to 5 meters or 16 feet in total length. As for its weight, it has been estimated at almost 5 tons, far more than the rhinoceros we come across today. A distinctive feature on its snout is a pair of blunt horns, more prominent in males. This distinction suggests brawling social behavior during rutting periods, with head-to-head combat. Nevertheless, this colossus, with its huge muscles to support its heavy skull, posed little danger to its contemporaries, especially as it was a herbivore. Indeed, Megacerops possess fleshy lips and a long tongue, attributes well suited to selecting its food, which consisted mainly of tender shoots and leaves. Many vegetarian animals thrived on this inexhaustible resource. In addition, leafy trees, increasingly abundant on the planet, offered abundant food to those who could get close to them, or even better, climb them. The Eocene thus marks a turning point in the history of our primate ancestors. It was during this period that these creatures, reminiscent of today's lemurs, established themselves in the canopy. The canopy is made up of a dense network of prodigiously leafy and fruit-bearing branches. The forests of the Eocene, with their abundant deciduous trees, became the ideal setting for major evolutions. The treetops became havens of peace, where small mammals and birds could feed without fear of predators lurking on the ground. In this suspended paradise, the ancestral primates undergo a metamorphosis. Their eyesight adapts to distinguish the nuances of ripe fruit. Their limbs evolve. The legs are transformed into prehensile feet, greatly improving their ability to move from tree to tree. An emblematic feature of these dexterous legs was born: the opposable thumb. This invaluable tool for grasping and manipulating paves the way for the dexterity that has characterized primates down the ages. Whether they lived in North America, Africa, or Asia, Eocene primates already possess several attributes characteristic of this group. Their feet, now capable of grasping, end not in claws but in nails. As for their eyes, they are protected by a bony structure and face forward, enabling binocular vision for the first time. These two features are reminiscent of a certain hominid you know very well, aren't they? During this particularly propitious period, the fauna continued its slow diversification. New orders of mammals appeared. These include the lagomorphs, the ancestors of our rabbits and hares, and the chiropterans. Indeed, the oldest recorded bat dates from this same period. All this could almost make us forget the cruelty that must have reigned in those days. Let's not forget that on the ground, as everywhere else, the law of the strongest dominates. In this now well-established food chain, one mammal became one of the most impressive predators of the Eocene. Belonging to the group of ungulate quadrupeds of Paleocene origin, it is Andrewsarchus, probably the largest terrestrial carnivorous mammal of this period. The only fossil of this colossus discovered to date was in Mongolia. It consists of a skull measuring around 90 centimeters or 35 inches long. This dimension suggests that the size of this animal must have been out of the ordinary in its class. Indeed, Andrewsarchus must have reached 4 meters or 13 feet in length and weighed close to 800 kilograms or 1,800 pounds. Compared with the new orders of mammals that have recently appeared, most of which weigh no more than 10 kilograms or 22 pounds, this was undoubtedly one of the most imposing. Roaming the plains, this fearsome animal fed in part on the large herbivores that shared its habitat, although some fossils suggest it may even have been omnivorous. But while the oceans and lands saw all kinds of animal and plant species proliferate insidiously, the planet was preparing for a new metamorphosis. Indeed, the extreme global warming that marked the beginning of the Eocene lasted no more than 100,000 to 150,000 years. This was followed by what geologists call the Eocene climatic optimum, which lasted nearly 5 million years. This climatic episode, the warmest of the Cenozoic era, lasted from around -54 to -49 million years. During these 5 million years, surface temperatures differed only slightly from those on the ocean floor, and as mentioned earlier, seasons showed little contrast. As this period drew to a close, a first upheaval took place in one part of the globe. While the Earth's poles were free of ice and aquatic ferns reigned supreme, a biological event was to influence the climate of the entire globe. It's the Azola event. Due to the Earth's tectonic configuration some 49 million years ago, the Arctic Ocean is virtually isolated from other oceans. The warm, windy climate in this part of the world favors evaporation. As a result, the density of the ocean increases, generating heavy precipitation on land. The rivers flowing into the ocean brought with them large quantities of fresh water and consequently nutrients. In the form of a thin, low-density nepheloid layer, these components covered the ocean, enabling the development of an aquatic fern, Azola. All the conditions were ripe for this plant to proliferate. In the space of 800,000 years, carpets of Azola covered almost 4 million square kilometers of the Arctic Ocean. On long, sunny days, the photosynthesis process begins to reduce the density of carbon in the atmosphere. More importantly, as these floating ferns die, they settle to the bottom of the ocean in an anoxic, oxygen-free environment, where they are protected from decomposition. Together, these two mechanisms trap almost 80% of the CO2 that was previously highly concentrated in the atmosphere. This considerably reduced the greenhouse effect, which was particularly significant at the beginning of the Eocene. In less than a few million years, ice appeared in the Arctic, whereas average temperatures dropped from 13 degrees Celsius, or 55 degrees Fahrenheit, to -9 degrees Celsius, or 15 degrees Fahrenheit. Nevertheless, the global climate remained warm overall, even if it tended to cool slowly throughout this period, until another drastic event occurred. For 34 million years ago, the Eocene came to an end. Once again, life experienced a major crisis. This unfortunate parenthesis, known as the Great Divide, corresponds to a new mass extinction. A major reshuffling of the fauna affected mainly terrestrial species. The causes of this umpteenth biological crisis are diverse, and still the subject of debate among scientists. A sudden global cooling of the planet, at least on a geological scale, is undeniable. Indeed, the end of the Eocene is marked by a rapid drop in temperature of the order of 4 degrees Celsius, or 7 degrees Fahrenheit, in just 500,000 years, concomitant with a significant drop in sea level. At the same time, the Drake Strait separating South America from Antarctica formed, opening the way for a cold current to circumnavigate the globe. Antarctica, totally isolated, gradually became covered by a perennial ice cap. The whole planet cools and a new ice age begins. While snow began to fall in the polar latitudes, over time it moved closer to the equator. First at high altitude, on the summits of newly formed mountains, then on the plains. Seasons are now very distinct, especially in Eurasia and North America, where harsh winters follow summer droughts. Warm tropical forests are now confined to the equatorial belt, while temperate zones are seeing the development of a new type of vegetation. Conifers and deciduous trees now populate these areas, but these forests, identical to those found in northern Europe and Canada, are not as welcoming as their predecessors. During the cold season, fruit, berries, and tender foliage are scarce, forcing species inclined to migrate to leave their homes. As for the rest, it appears that 50% of Europe's endemic mammal fauna became extinct during this event, replaced by immigrant species from Asia. On a more global scale, this reshuffling of the fauna affected land masses located in mid-latitudes, where the climate changed from tropical to temperate. On a global scale, scientists have dubbed this new biological crisis the terminal Eocene event. But what could have caused this cooling? Can the Antarctic circumpolar current, known as the most important ocean current on the planet, explain this global cooling on its own? While it is undeniable that the Antarctic circumpolar current has played a major role, other causes may explain this global drop in temperature. The main current theory is the decrease in atmospheric carbon dioxide. The latter would have declined slowly from the middle to the end of the Eocene, due in part to the strong alteration of silicates in warm climates. Alteration of silicates, which account for 97% of the rocks in the Earth's crust, is a set of reactions known to consume large quantities of CO2. In addition, widespread volcanic activity, possibly caused by the Ethiopian high plateaus or Ethiopian traps, may have contributed to the onset of a new volcanic winter. Finally, the fall of several meteorites has also been suggested. Various craters dating from the same period, identified in Chesapeake Bay in the USA, or the Papagai crater in central Siberia, support this theory. But if the Great Divide is marked by this major climatic event, another phenomenon is responsible for the extinction of numerous species. The migration of animal species must also be taken into account. This intercontinental transhumance, due to the change in weather, was made possible by another phenomenon. These include changes in interactions between certain continents. The drying up of the Turgai Inland Sea, which had previously separated Europe from Asia, opened up new horizons for Asian fauna. This led to a major migration of Asian fauna to present-day Europe. The local European fauna, somewhat different with less corpulent specimens, underwent a considerable impact, which, coupled with this period of glaciation, resulted in a significant renewal of species, leading to a mass extinction. This migratory movement also took place in North America and Africa, these continents not spared by the new meteorological conditions. While some species fail to survive and disappear, others newly arrived are confronted with the need to adapt to a different living environment. But fortunately, following the principles of natural selection, some succeed in adapting, even diversifying and evolving. Here we are at the third and final Paleogene epoch. This period is known as the Oligocene. Subdivided into two geological stages, the Riparian and the Cetetian, it extends from -33 to -23 million years BC. The Oligocene marks the transition between the tropical Eocene and the more modern Miocene ecosystems. During this third Paleogene epoch, the landscape changes once again. Once again, flora and fauna had to adapt to survive. Tropical and intertropical forests are replaced by temperate deciduous forests, and grasses begin to spread from the banks of rivers and lakes. Monocotyledons, i.e. grasses, became highly diversified for the first time, even colonizing certain territories, which were thus covered with immense grasslands. Lands at high and mid-latitudes, once home to tropical rainforests, are now occupied by rich savannas, sometimes consisting of vast expanses of grass, sometimes of inviting forests. In these environments where colorful flowering plants are multiplying as never before, insect diversification continues. Already present in dinosaur times, three groups continue to evolve. These include Coleoptera, to which beetles and ladybugs belong, Diptera, such as flies and mosquitoes, and Hymenoptera, from which bees and wasps have evolved. But with such a proliferation of flowering plants, another group, hitherto almost invisible, is multiplying for the first time. This is the group of Lepidoptera, or butterflies. Marine and terrestrial fauna are becoming more modern, and new forms adapted to open savanna-type habitats are emerging. Nonetheless, these changes in the populations took place smoothly, prompting scientists to describe the period as a quiet one. Indeed, although the mammalian fauna underwent significant reorganization during the Oligocene, particularly in Europe, communities remained relatively stable. Grazing mammals underwent significant evolutionary radiation. As a result of this rapid evolution, many artiodactyls and perissodactyls replaced the dominant Eocene species. The Entelodon magnus is one of the fascinating creatures of this period in Europe, Asia, and North America. Measuring nearly 3.5 meters or 11 feet in length, this massive member of the artiodactyl family weighs up to a ton. Probably omnivorous, it is able to crush bones and consume large chunks of flesh. to the detriment of the chalicotheres, those half-horse, half-gorilla animals, and camelids it mingles with. With its impressive canines and robust stature, Entelodon magnus was able to rival other large carnivores of its time, such as Hyenodon. This feline-like creodont, whose name literally means hyena tooth, ranges in size from 30 centimeters or 12 inches to 1.4 meters or 4 feet. Its undisputed strong point is its speed, which can reach 55 kilometers per hour or 34 miles per hour. This is a considerable advantage over its main rival, which is much slower. But the animal that most symbolizes Asian migration is certainly the rhinoceros. 3 families of rhinoceros, or horns on their noses, appeared at the same time. Some were much more graceful than today's rhinos, with slimmer bodies and thinner legs, and were good runners despite their size. They belong to the Hyraconodontidae family. We also find the Rhinocerotidae, which are smaller and prefer to live in herds. As for the Aminodontidae, they resemble hippopotamuses and feed on aquatic plants. But it's in Asia that we must turn our gaze to meet the largest mammal of all time. This rhinoceros giraffe, of the learned name Indricotherium, a close relative of the rhinoceros, shows off its incredible stature, measuring over 5 meters or 16 feet in height, 8 meters or 26 feet in length, and weighing up to 15 tons. However, despite its size, this mastodon is not a predator. Its massive heavy head means it can't even graze on pasture. The fauna that developed abundantly during the Oligocene was distributed across the globe. However, South America, still isolated from the other continents, is home to a distinct fauna. One of the emblematic animal species of this period is the Pyrotherium. It resembles an elephant with massive limbs, tusks, and a trunk. Another notable species from this continent is the boar hyena. This carnivorous predator, like today's Australian hyenas, is particularly adept at running and is extremely fearsome to its fellow creatures. Among the predators present during the Oligocene, Vasuki indicus is a colossal snake that could well dethrone the famous Titanoboa. The only specimen recently discovered in the Naredi Formation, located in the Indian state of Gujarat, is probably the largest snake ever to have existed on the planet. Imagine a reptile as long as a school bus. According to paleontologists who have had the privilege of studying the 27 giant fossilized vertebrae of this creature, its length is estimated at 15 meters or 50 feet. These vertebrae suggest that this wide-bodied, cylindrical crawling monster, resembling a giant python, could have weighed close to a ton. Near the swamps where this non-venomous snake mastered the art of concealment, woe betide any prey approaching this ambush. Once seized under the effect of a Herculean constriction, their slow agony was prolonged until certain death before they were ingested. Several factors probably contributed to the existence of such a large, cold-blooded animal. For scientists, higher temperatures than we know today, together with the absence of indigenous predators, represent particularly favorable conditions. What's more, given the numerous fossils discovered nearby, including crocodiles, turtles, and fish, there seemed to be no shortage of relatively abundant food. In short, the Vasuki indicus evolved in an environment that was particularly conducive to its development. If the terrestrial landscape underwent major changes during the Oligocene, so did the marine environment. The Tethys Ocean, once a sanctuary for marine life, gradually shrank. This monumental change has led to the collapse of its previously richly biodiverse ecosystem. The seas around Southeast Asia and Australia have become the new epicenters of marine diversity. In the face of this upheaval, a large proportion of marine life was unable to survive. Nearly 97% of marine snails, 89% of clams, and half of Gulf echinoderms have disappeared. Despite the appearance of new species, overall diversity suffered a notable decline. Mollusks adapted to cold waters undertook a colossal journey, moving along the Pacific coast from the distant seabeds of Alaska and Siberia. Oligocene oceans began to reflect the fauna we know today, with the appearance of calcareous ceratuluids, a family of worms, and the abundance of bivalves such as mussels and oysters. Small, colorful parrotfish appeared and diversified, particularly in the Indo-Pacific. Similarly, during the Oligocene, baleen and toothed whales emerged, while their ancestors, the archaeocet cetaceans, failed to adapt to increasingly cold and opaque waters. Lacking echolocation, a sonar system enabling them to locate their prey, or any obstacles at all, these old-world cetaceans eventually declined. All the more so, as competition with modern cetaceans and razorback sharks has never been tougher for them. Other newcomers among marine mammals include Behematops, a hippopotamus-like herbivore whose genus is now extinct, or pinnipeds, semi-aquatic mammals with flipper-like legs, such as the otter-like Pugilla darwini. This animal, measuring around 1 meter or 3 feet in length, is considered a transitional form between the terrestrial ancestors of pinnipeds and present-day species such as seals or sea lions, which are totally aquatic. But as life once again emancipates itself, having successfully thwarted upheavals of every kind, what's next? For 23 million years ago, the Paleogene gave way to an unprecedented period. What mysteries lie behind the end of this first Cenozoic period? Whatever the case, each denouement is only the prelude to a new beginning, as the geological timescale testifies. As we close the chapter on the Paleogene, the post-dinosaur era, we can only marvel at the resilience and adaptability of life on Earth. This period, marked by drastic climatic changes and geological upheavals, was the scene of unprecedented evolution. From the depths of the oceans to the treetops, every species has played its part in this great symphony of biodiversity. We have seen entire ecosystems transformed, lineages extinguished, and new life forms emerging, ready to conquer unexplored realms. Above all, mammals have undergone unprecedented diversification and expansion. Small mammals evolved rapidly to occupy many specific habitats, while larger ones began to dominate terrestrial ecosystems. Marking the advent of an era dominated by mammals, the Paleogene teaches us that despite the challenges, life always finds a way to maintain itself and even transform itself. Seen from the sky, in a million years' time, the Earth won't change that much. Sure, the continents will move, but no more than 45 to 60 kilometers or 30 miles from their current locations. The sun will continue to shine, rising every 24 hours, and the moon will orbit the Earth in about a month. But some things will change quite fundamentally. In many parts of the world, irreversible geological processes are transforming the landscape. The vulnerable contours of ocean coasts will change particularly markedly. An active submarine volcano off the southeast coast of the largest of the Hawaiian Islands has already risen above 3,000 meters or 10,000 feet from the ocean floor and is growing every year. In a million years, a new island will rise from the ocean waves, already named Lohi. At the same time, the extinct volcanic islands to the northwest, including Maui, Oahu, and Kauai, will shrink under the influence of wind and ocean waves respectively. With regard to waves, those studying rocks for future changes conclude that the most active factor in changing the Earth's geography will be the advance and retreat of the ocean. A change in the rate of rift volcanism will take a very, very long time to affect this geography, depending on the amount of lava more or less solidified on the ocean floor. Sea level can fall significantly during lulls in volcanic activity, when the rocks at the bottom cool and settle. Scientists believe this is what caused the sharp drop in sea level just before the Mesozoic extinction. The presence or absence of large inland seas such as the Mediterranean, as well as the reunion and breakup of continents, led to major changes in the size of coastal shelf areas. To imagine the world a few 100 million years from now, we need to look to the past for clues to understanding the future. Global tectonic processes will continue to play an important role in changing the face of the planet. Today, continents are separated from one another. Vast oceans separate America, Eurasia, Africa, Australia, and Antarctica. But these immense expanses of land are in constant motion, and their speed is around 2 to 5 centimeters or 2 inches per year, i.e., around 1,500 kilometers or 930 miles in 60 million years. We can establish fairly precise vectors of this movement for each continent by studying the age of the basalts on the ocean floor. Basalt near mid-ocean ridges is quite young, no more than a few million years old. By contrast, the age of basalt near continental margins and subduction zones can reach over 200 million years. It's easy to take into account all these age data on the composition of the ocean floor to rewind the tape of global tectonics over time and to get an idea of the geographical mobility of the terrestrial continents over the last 200 million years. Based on this information, it is also possible to project the movement of continental plates 100 million years in advance. Given the current trajectories of this movement across the planet, it appears that all continents are heading for the next collision. In 250 million years, most of the Earth's landmass will once again become a giant supercontinent. Nevertheless, the exact structure of the future supercontinent remains the subject of scientific controversy. It is possible to take into account the current movements of the continents and predict their trajectory over the next 10 to 20 million years. The Atlantic Ocean will expand by several hundred kilometers or miles, while the Pacific Ocean will shrink by around the same distance. Australia will move north towards South Asia, and Antarctica will move slightly away from the South Pole towards South Asia. Africa will move slowly northwards across the Mediterranean Sea. In a few tens of millions of years, Africa will collide with southern Europe, closing the Mediterranean Sea and erecting a Himalayan-sized mountain range at the site of the collision. So the map of the world in 20 million years' time will look a little familiar. When modeling a map of the world 100 million years from now, most researchers identify common geographic features. For example, agreeing that the Atlantic Ocean will exceed the size of the Pacific Ocean and become the largest water basin on Earth. According to the extraversion theory, the Atlantic Ocean will continue to open up, and the Americas will eventually collide with Asia, Australia, and Antarctica. In the final stages of this supercontinent assembly, North America will close the Pacific Ocean to the east and collide with Japan, and South America will wind clockwise from the southeast, joining the equatorial part of Antarctica. All these parts are astonishingly combined with each other. Thus, the new supercontinent will be a single continent, stretching from east to west along the equator. The extraversion model mainly maintains that the large convection cells in the mantle, located beneath the tectonic plates, will remain unchanged in their current form. In contrast, the alternative approach, known as introversion, takes the opposite stance, referring to past cycles of closure and opening of the Atlantic Ocean. Today, both supercontinent theories, extraversion and introversion, remain popular. Whatever the outcome of this discussion, everyone agrees that while in 250 million years, the Earth's geography will change significantly, it will still reflect the past. According to some simulations, in around 200 million years' time, average temperatures on Earth should fall slightly below 12 degrees Celsius or 53 degrees Fahrenheit. At the same time, global sea levels will fall by around 200 meters or 650 feet. In this configuration, conditions for the development of complex life will remain quite favorable at low and mid-latitudes. Only after around 400 million years will average surface temperatures fall to around 10 degrees Celsius or 50 degrees Fahrenheit, and ocean levels drop by more than 500 meters or 1,640 feet from their current position. In this situation, all continents from north to south, even at moderate latitudes, will be covered by glaciers, and mountainous regions at equatorial latitudes will also be frozen. However, this cold snap will not be permanent. After a further 200 to 300 million years or so, an equilibrium should be established between the decrease in temperature due to the bacterial elimination of nitrogen from the atmosphere and the increase in the sun's luminosity. The temporary assembly of continents around the equator will mitigate the impact of ice ages and moderate changes in sea level. Where continents collide, mountain ranges will rise, climate and vegetation will change, and oxygen and carbon dioxide levels in the atmosphere will fluctuate. These changes will be repeated throughout Earth's history. A gamma-ray burst, or huge supernova, occurs less than 6,500 light-years from Earth within 500 to 600 million years, gamma-ray bursts are enigmatic phenomena that appear to be the most intense and energetic explosions in the universe, and astronomers assume that they are linked to extremely powerful supernovae. Fortunately, we have yet to observe a gamma-ray burst close enough to us to fully understand what is happening. So far, gamma-ray bursts have only been detected in other galaxies. But if such an event were to occur close to home on a cosmological scale, as it will in around 500 million years' time, less than 6,500 light-years from Earth, it could lead to a mass extinction. A gamma-ray burst directed in our direction, lasting just 10 seconds, could destroy at least half of the Earth's ozone layer. Large-scale ozone depletion could have devastating consequences on food chains, leading to the death of many species. A gamma-ray burst would annihilate life forms on the Earth's surface and in the upper layers of the ocean, which currently supply significant quantities of oxygen to our atmosphere. It turns out that gamma rays also decompose the oxygen and nitrogen present in the atmosphere. These gases would be transformed into nitrogen dioxide, better known as smog. This would envelop the sun over heavily polluted areas. If this smog were to cover the entire Earth, it would block out sunlight and trigger a global ice age. Due to tidal forces, the Moon has moved more than 20,000 kilometers or 12,000 miles away from the Earth. Even in the most favorable cases, the lunar disk can no longer completely cover that of the Sun. In 600 million years' time, all eclipses will be annular. The fate of the Earth is intimately linked to that of the Sun, which, like other stars, cannot shine forever. 50 million years after the Sun's formation, our star became a main sequence star. Since then, its luminosity has increased in an almost linear fashion, rising by around 1% every 110 million years. Within 600 million years, our Sun will undergo a gradual transformation, resulting in a progressive increase in both brightness and heat. This increase in the Sun's luminosity will have a significant impact on our planet, resulting in more solar radiation reaching the Earth. This increase will have an impact on the silicate minerals present on the planet, leading to increased weathering of these minerals. This, in turn, will affect the carbonate-silicate cycle, which is a geochemical process involving the interaction between carbonate and silicate. Increased weathering of surface rocks traps carbon dioxide in the soil in the form of carbonate. As water evaporates from the Earth's surface, rocks harden, leading to a slowdown in plate tectonics, which eventually comes to a halt when the oceans completely evaporate. With less volcanism to recycle carbon into the Earth's atmosphere, carbon dioxide levels begin to fall. For hundreds of millions of years now, the Earth has been experiencing a period of intense cold, with an average surface temperature of around 10 degrees Celsius or 50 degrees Fahrenheit. But now, the Sun's increasing brightness is triggering a rise in the Earth's temperature, generating a series of problems. The first signs of trouble will appear within 600 million years, but it's only when the average temperature reaches 47 degrees Celsius or 117 degrees Fahrenheit, when solar luminosity is 10% higher than at present in 1.1 billion years' time, that the situation will become critical. From that point onwards, the Earth will begin to lose water progressively, resulting in a modification of its atmosphere and becoming a humid greenhouse due to the massive evaporation of surface water. At this point, the amount of water in the stratosphere should increase. These water molecules will be broken down by the sun's ultraviolet radiation via the process of photodissociation. As a result, hydrogen will escape from the atmosphere. The main result should be the disappearance of the oceans in around 1.1 billion years. This water vapor, raised in the stratosphere, will undergo chemical decomposition, separating into oxygen and hydrogen. This is when major changes will take place. Higher temperatures will cause the oceans to absorb more carbon dioxide, a gas essential to plant life. This absorption will reduce the amount of carbon dioxide in the atmosphere, causing an imbalance in the plant life cycle. It is estimated that the planet will be able to support highly organized life for another 600 million years from now, as current forecasts indicate that after this period, the sun's increasing brightness will have a significant impact on the biosphere. The emerging scenario is therefore worrying, as not only will the Earth progressively lose its precious water, but also gas is vital for plant development. Together, these elements threaten the delicate balance of our ecosystem. The high temperatures projected for the future would cause the oceans to absorb more carbon dioxide, which would disrupt the biological processes essential to plant life, accelerating the problems associated with water loss and the degradation of our atmosphere. We will be approaching the Earth's carbon dioxide compensation limit, a critical point at which the balance between carbon dioxide and oxygen becomes unsustainable for photosynthesis. In around 600 million years' time, carbon dioxide levels will be lower than those needed to maintain the C3 carbon fixation by photosynthesis used by trees. Some plants, using C4 carbon fixation, can survive carbon dioxide concentrations as low as 10 ppm. Currently, 99% of plants use C3 photosynthesis. Their ability to convert sunlight into energy is gradually declining, leading to a general decline in plant biomass. If atmospheric CO2 levels fall, the survival of embryophytic plants becomes difficult, as they require a minimum concentration of around 10 ppm atmospheric CO2. It is highly probable that the evolution of living organisms will enable a certain number of organisms to adapt to these conditions by using a more efficient photosynthetic carbon acquisition mechanism. When levels fall below this value, complex plants begin to die, leading to a reduction in oxygen production. This decrease, combined with continued consumption by biota and oxidation of kerogen, which is organic carbon in sedimentary rocks, leads to a gradual decline in the atmospheric oxygen until it reaches zero within a few million years. Researchers estimate that plants that use the C3 photosynthesis process to fix atmospheric carbon dioxide should disappear in 600 million years, and C4 plants in 840 million years at the latest, due to the loss of carbon dioxide from the atmosphere. This massive disappearance of plants would have devastating consequences for all living beings as we know them today. Plants are at the very base of the food chain providing food and energy for herbivores. Their decline means fewer food resources for herbivores, which in turn suffer adverse consequences. Their populations begin to decline, upsetting the balance of ecosystems. Without plants to produce oxygen through photosynthesis, animals would face a disastrous situation. Large endothermic animals, such as mammals and birds, would probably be the first to disappear, due to their higher oxygen requirements, compared to smaller, endothermic and ectothermic animals. As atmospheric oxygen levels fall and temperatures rise, placental mammals will become particularly vulnerable. Not only do they have higher oxygen requirements than non-placental mammals, but embryonic development is also highly sensitive to excessive heat. Large herbivorous mammals would suffer from diminishing food resources as plant availability declines. Small mammals would be slightly less affected due to their lower oxygen requirements and surface-to-volume ratio, which facilitates heat dissipation. Placental mammals experience higher body temperatures than marsupials and monotremes, making them potentially more sensitive to rising temperatures. Birds may be better adapted to survival than larger mammals, as their generally smaller size means they need less oxygen. What's more, migratory birds in particular would be better equipped than animals of a similar size, thanks to their ability to travel long distances in search of cooler refuges. Nevertheless, the number of such refuges would decrease as temperatures continue to rise. These refuges would also be likely to be found at higher altitudes, where less land surface would be available, limiting population size as species migrate to higher altitudes. Ectothermic vertebrates such as fish, amphibians, and reptiles could survive longer than endothermic animals in this scenario, thanks to their better heat tolerance and generally lower oxygen requirements. However, reduced water availability would make some amphibian species more vulnerable in such an environment. Fish species would also be at risk, although rapid evaporation from the oceans would not occur at this stage. Marine species may have a better survival capacity than freshwater species due to the greater volume of ocean water compared with freshwater. For ectotherms, ambient temperature influences their metabolic rate. An increase in ambient temperature would lead to an increase in metabolic rate, and therefore a greater need for food. As a result, surviving species could be exposed to starvation. Reptile species whose sex determination depends on temperatures would be more sensitive to rising temperatures. Invertebrates could be the last animals on Earth before all animal species disappear. Some insects, such as beetles, can survive temperatures of up to 56 degrees Celsius, or 133 degrees Fahrenheit. In general, terrestrial life would initially be more vulnerable than marine life, due to the regulating effects of water temperature. However, the loss of terrestrial vegetation would lead to a reduction in nutrients reaching the oceans. Isolated communities in marine ecosystems, such as animal populations living near volcanic vents, would probably survive longer. Depending on the half-life of oxygen in the atmosphere, animal life could persist for up to 100 million years after the disappearance of plants. Some cyanobacteria and phytoplankton could survive without plants, as they are able to tolerate carbon dioxide levels as low as 1 part per million. they could persist until the atmosphere becomes too depleted of carbon dioxide to allow any form of photosynthesis. In one study, researchers claimed that a specific form of animal life could persist even after most plant life on Earth had disappeared. They used fossil evidence from the Burgess Shale in British Columbia, Canada, to study the climate of the Cambrian explosion, and used it to predict the future climate when global temperatures would rise due to a warming sun and decreasing oxygen levels, leading to the ultimate extinction of animal life. Initially, they expected some insects, lizards, birds, and small mammals to persist, as well as marine life. However, without a continuous supply of oxygen from plant life, they estimated that animals would probably die of asphyxiation. Even if enough oxygen were to remain in the atmosphere, thanks to the persistence of some form of photosynthesis, steadily rising global temperatures would lead to a progressive loss of biodiversity. As temperatures continue to rise, the last animals will be forced to move to the polar regions, or even underground. They would mainly be active during polar night periods, and would go into aestivation during polar day periods due to the intense heat. Much of the Earth's surface would become an arid desert, and life would concentrate mainly in the oceans. However, due to a decrease in the input of organic matter from the land and a reduction in dissolved oxygen, marine life would also disappear, following a similar pattern to that of the land surface. This process would begin with the loss of freshwater species and end with the invertebrates, particularly those not dependent on living plants, such as termites, or those found near hydrothermal springs, such as worms of the Riftia genus. Without CO2, photosynthesis can no longer take place. Without plant life to recycle oxygen back into the atmosphere, free oxygen and the ozone layer will disappear from the atmosphere, allowing intense levels of deadly UV light to reach the surface. As a result of these processes, multicellular life forms could become extinct in around 800 million years, and eukaryotes in 1.3 billion years, leaving only prokaryotes. To meet the sun's energy needs, the nuclear fusion reactions taking place at its core convert around 500 tons of hydrogen into helium every second. The main effect of this alchemy is a progressive reduction in the number of particles of energy the sun releases. This is why the sun's luminosity increases with the passage of time. Thanks to an effective greenhouse effect, the Earth has maintained a stable temperature, apart from a few periods of glaciation, which have enabled life to evolve on its surface. For hundreds of millions of years, the Earth has not undergone any significant change in its ocean mass, thanks to the near equilibrium of mantle water inflows and outflows. To maintain water in a liquid state on our planet, it is essential to establish a balance between the solar energy absorbed and that emitted, enabling us to maintain adequate temperatures. This balance is crucial to the survival of life as we know it. When the amount of greenhouse gases in the Earth's atmosphere increases, as is currently the case, a new energy balance is created, where the greenhouse effect creates an additional blanket, causing the surface to warm up. The Earth has an integrated regulating mechanism called the carbonate-silicate cycle, which controls the amount of carbon dioxide in the atmosphere to maintain a stable climate. Unfortunately, Unfortunately, this cycle operates on a timescale of the order of 1 million years, making it too slow to be an effective solution for the current global warming problem we humans face. Progressively, even during the current calm period of hydrogen combustion, the Sun is inexorably rising in temperature. Some 4.5 billion years ago, at the very beginning, its luminosity was equivalent to 70% of today's level. By the time of the Great Oxygen Event some 2.4 billion years ago, its brightness had already reached 85% of today's level. For the next billion years, the Sun will continue to produce nuclear energy by converting hydrogen into helium. This is what almost all stars do most of the time. As the Sun converts hydrogen to helium in its core, the average molecular weight increases, leading to a rise in core temperature and the speed of the fusion reaction, known as the proton-proton chain. This gradually leads to an increase in the star's energy release. As a result, the Sun will shine even brighter. When the amount of incoming energy increases, it can also contribute to global warming. This is precisely what happens when the Sun's brightness gradually increases. Although the Earth's climate may experience shorter-term variations due to the seasons, changes in atmospheric composition, such as the addition of man-made greenhouse gases, as well as factors such as volcanic dust and Milankovitch cycles, the Earth's surface is experiencing a slow but steady warming due to increasing solar luminosity. Over a period of time, perhaps even several 100 million years, the Earth's feedback may attenuate this effect. The greater the thermal energy, the more intense the evaporation, hence the increase in cloud cover, which contributes to the reflection of most sunlight back into space. Increased thermal energy means faster weathering of rocks, greater absorption of carbon dioxide, and lower levels of greenhouse gases. Thus, negative feedbacks will preserve life-supporting conditions on Earth long enough. At some point, the Earth's atmosphere will reach a threshold where it will no longer be able to maintain a stable energy balance, leading to an amplification of the greenhouse effect. This phenomenon is often likened to a runaway greenhouse, characterized by positive feedback. As the planet's surface warms up, water evaporation from the atmosphere increases. Water is a powerful greenhouse gas, which reinforces the greenhouse effect and further warms the planet's surface. For several million years, cellular life can persist in such conditions. However, the critical moment will inevitably arrive when the greenhouse effect becomes uncontrollable, warming the Earth's surface to the point where the oceans reach a state of complete evaporation. Despite the increased amount of water vapor near the Earth's surface, there will be no liquid ocean left. After that, it will only take a few 100 million years for the oceans to evaporate, transforming the atmosphere into an endless pool of steam. When ultraviolet light interacts with atmospheric gas, it can cause the gas to heat up further, meaning that more heat is transferred to atmospheric water when it interacts with extreme ultraviolet light. As a result, the water absorbs more energy and heats up faster. This leads to an increase in water evaporation, and consequently, a more rapid loss of water from the Earth's surface. Another way of explaining this is to use the concept of the habitable zone, which refers to the orbital region around a star where a planet can maintain liquid water, provided it has a suitable atmosphere. At present, the inner edge of the Sun's habitable zone is around 95% of the distance between the Earth and the Sun. Our planet will then be completely devoid of life, but the real apocalypse will come later. As the Sun's luminosity increases, the inner edge of the habitable zone will move progressively further out. It's hard to say exactly when the inner edge of the habitable zone will reach the Earth's orbit, but it's estimated to be around 1 billion years. Some extremophiles may still live in refuges at higher latitudes or deep underground, but these will only be ephemeral remnants of a once exuberant biosphere, a situation that could recall the attractive symmetry of life's beginnings on Earth. In all likelihood, Earth will follow the fate of Venus, becoming a hot, barren world. As the habitable zone of our Sun has shifted towards the outer solar system, Mars is now located in this zone. It is possible that Mars's surface temperature will gradually rise. Carbon dioxide and water currently frozen beneath the Martian soil will be released into the atmosphere, creating a greenhouse effect. This will warm the planet until it reaches conditions comparable to those on Earth today, potentially offering a new island for life. According to computer models, the Moon's presence seems to stabilize the Earth's obliquity, helping to avoid dramatic climate changes. This stability is due to the fact that the Moon accelerates the precessional motion of the Earth's rotational axis, preventing resonances between the precession of the rotation and the precession of the planet's orbital plane. The tidal acceleration caused by the Moon slows the Earth's rotation and increases the distance between the Earth and the Moon. As the semi-major axis of the Moon's orbit continues to increase, this stabilizing effect will diminish. At some point, the disturbances will probably lead to chaotic variations in the Earth's obliquity, and the tilt axis could tilt to angles as high as 90 degrees to the plane of the orbit. This is estimated to happen between 1.5 and 4.5 billion years ago. High obliquity would probably lead to dramatic climate changes and could compromise the planet's habitability. When the Earth's axial tilt exceeds 54 degrees, annual insolation at the equator becomes lower than at the poles. It is possible for the planet to maintain an obliquity of 60 degrees to 90 degrees for periods as long as 10 million years. The likely consequence is that ocean evaporation, plate tectonics, and the entire carbon cycle will come to an end. This could happen in around 2 to 3 billion years' time, when the planet's magnetic dynamo could cease to function, leading to the decomposition of the magnetosphere. This would lead to an accelerated loss of volatile elements from the outer atmosphere. In 2.8 billion years, the Earth's surface temperature, even at the poles, averages 147 degrees Celsius, or 297 degrees Fahrenheit. Life is reduced to single-cell colonies in isolated and scattered microenvironments, such as underground caves, and dies out everywhere else. Every second, the Sun emits a solar wind in the direction of our planet, corresponding to a flow of 1 million tons of protons and electrons. These particles are stopped in their tracks by the Van Allen belts, the Earth's magnetic field. Stretching over 70,000 kilometers or 43,000 miles, it originates from the Earth's iron-nickel core. The core is composed of a solid part, the seed, and a liquid layer 2,000 kilometers or 1,240 miles thick. The uninterrupted stirring of the liquid metal layer leads to the formation of the magnetic field. At present, the radius of the inner core is increasing at an average rate of around 0.5 millimeters per year, at the expense of the outer core. Virtually all the energy required to power the dynamo is supplied by the inner core. Within 3 billion years, the inner core is expected to absorb most, if not all, of the outer core, resulting in an almost entirely solidified core composed mainly of iron and other heavy elements. The remaining liquid envelope will consist mainly of lighter elements that will undergo less mixing. Tectonic plate dynamics are generated by the transfer of heat from the Earth's core to the surface. This heat transfer takes place through the mantle by convection, sometimes combined with thermal conduction. When heat plumes reach the crust, they reach their heat and are pushed out by new hot plumes. This horizontal movement in the upper mantle is the driving force behind the movement of tectonic plates. However, as the Earth cools over time, the liquid outer core gradually solidifies. This solidification reduces convection in the mantle, limiting the power available to move the plates. Eventually, after around 3 billion years, convection will cease completely, putting an end to tectonic plate movements. If plate tectonics cease at some point, the Earth's interior will cool less efficiently, slowing or even halting the growth of the inner core. In both cases, this could lead to the loss of the magnetic dynamo. Without a functional dynamo, the Earth's magnetic field will weaken rapidly over a geologically short period of around 10,000 years. The disappearance of the magnetosphere will lead to increased erosion of light elements, notably hydrogen, from the Earth's atmosphere into space, creating conditions less conducive to life. In around 4 billion years, the increase in temperature at the Earth's surface will trigger an uncontrollable greenhouse effect, creating conditions even more extreme than those on Venus today. This will heat up the atmosphere and raise the surface temperature above 500 degrees Celsius or 932 degrees Fahrenheit, high enough to melt the planet's surface in some places. Nevertheless, much of the atmosphere will be retained until the sun enters its red giant phase. At that point, the Earth's biosignatures will disappear, to be replaced by signatures caused by non-biological processes. From then on, all traces of Earth's life history will be completely erased. In 4.5 billion years, interactions between the Andromeda Galaxy M31 and the Milky Way will form a new galaxy called Milkomeda. The Andromeda Galaxy, also known as M31, is a spiral galaxy containing up to 1,000 billion stars, compared with 300 to 400 billion for the Milky Way. Made up of gas and dust, it adopts a flattened disk shape and contains a bulge at its center. Originally located 2.55 million light-years away, the Andromeda Galaxy has always been the closest to the Milky Way. It has been gradually closing in on the Milky Way at a speed of 120 kilometers per second, or 75 miles per hour. At first, the two galaxies don't seem to have collided. Being so far apart, the stars will initially pass each other without colliding head-on, before moving apart. Sometime later, this apparent choreography leads to a new rapprochement, this time followed by a strong interaction between the two galaxies. Their orbits are strongly affected by the anarchy of gravitational forces in place during the galaxy's interpenetration. The result, after 2 billion years, is the birth of a gigantic system with little interstellar gas, a new galaxy, Milkomeda. Unlike its two parents, this new galaxy is elliptical in shape, and the stars it contains are scattered around a sphere. The Milky Way and M31 no longer exist. This collision will not disrupt the orbits of planets within the solar system. While the gravity of passing stars can detach planets in interstellar space, the distances between stars are so great that the probability of the Milky Way-Andromeda collision causing disruption to a given star system is negligible. Although the solar system as a whole could be affected by these events, the Sun and planets are unlikely to be disturbed. The new galaxy sees a new outburst of stars, but as the little remaining gas is rapidly consumed, star formation comes to a halt, and the new galaxy will slowly fade away as its new stars die out. In 5 billion years' time, the Sun will leave its main sequence and begin its transformation into a red giant, having exhausted the hydrogen reserves in its core. The energy released during the fusion of hydrogen nuclei in the Sun's core fuels the frenetic agitation of lively particles that exert a powerful outward pressure. It is thanks to this pressure that the Sun swells and does not collapse under its own weight. Until now, this balance has been maintained, but now at 5 billion years, this is no longer the case. Although the Sun still abounds in hydrogen nuclei, there are virtually none left in its core. Hydrogen fusion produces helium, whose nuclei are heavier and denser than those of hydrogen. It is in the core of the Sun that the temperature is highest, at around 15 million degrees Celsius, or 27 million degrees Fahrenheit. The fusion of hydrogen into helium requires 10 million degrees Celsius, or 18 million degrees Fahrenheit. On the other hand, helium fusion requires a temperature of the order of 100 million degrees Celsius, or 180 million degrees Fahrenheit. The Sun is nowhere near this threshold, so as helium replaces hydrogen in the core, the fuel supply for fusion will diminish. Pressure from energy production will decline, and gravity will prevail, causing the Sun to implode. As its gigantic mass collapses in on itself, the Sun's temperature will rise dramatically. Despite this pressure and extreme temperature, helium fusion is still not possible, and the hydrogen then triggers a second phase of fusion within a thin layer around the helium core. As hydrogen fusion proceeds at an inordinate rate, the thrust is much more intense than before. The Sun swells to colossal proportions, reaching over 100 million kilometers, or 62 million miles in diameter, almost 100 times its current diameter. Transforming into a pulsating red giant, it will become thousands of times brighter than it is today. It leaves its main sequence to become a red giant. Naturally, the planets in the solar system will be directly affected by this change. The Sun, with its diminished mass, exerts less gravitational attraction, enabling the planets to migrate to more distant orbits. But do the planets go far enough to win the race against the Sun's increasing diameter? Mercury loses the race, swallowed by the Sun and briefly vaporized. Mars, orbiting further out, escapes unscathed. Venus is lucky. The Sun stops swelling just before it reaches its new orbit, and at the same time, the Earth is also spared. Nevertheless, conditions are fundamentally different. Earth and Mars rotate synchronously with the Sun. The average temperature is now several thousand degrees. What does a sunrise look like from Earth today? Instead of a warm, cheerful yellow disk, a gigantic red circle slowly settles above the horizon. It won't be long before Mars suffers the same fate as Earth. The atmosphere begins to warm. Potential life forms on this planet won't survive another 1 billion years. 2 new orbits are now taking their place in our solar system's habitable zone, the orbits of Jupiter and Saturn. Although neither planet is conducive to life, either Jupiter with water in its clouds or Saturn made up entirely of gas, their respective moons could become suitable places for the appearance of primitive life once their temperatures have risen. In this way, simple organisms could see life on the surface of Saturn's moons, Enceladus or Titan, or Jupiter's moon, Europa. Most of the Earth's atmosphere will gradually be lost to space. The Earth's surface will be transformed into an ocean of lava, with floating continents of metals and metal oxides and icebergs of refractory materials. Surface temperatures will rise dramatically, exceeding 2,000 degrees Celsius or 3,632 degrees Fahrenheit. Then, over 12 billion years old, the Sun's most rapid expansion phase as a red giant will occur in its final stages in 7.4 billion years' time. At this stage, it is likely to expand sufficiently to reach a maximum radius of around 1.2 astronomical units. The Sun will have lost more than a third of its current mass, which will have dispersed in the form of an intense solar wind. This loss of mass will cause the orbits of each planet to expand considerably. Considering only this phenomenon, Venus and Earth could probably escape incineration, but other studies suggest that the 2 planets would still be absorbed due to tidal interactions with the tenuous gas of the Sun's expanded outer envelope. Forecasts for the end of our planet are therefore rather gloomy. The Earth's gravitational interaction with the Sun's outer atmosphere will cause the Earth's orbit to shrink. The drag effect of the Sun's chromosphere will progressively reduce the Earth's orbit. These effects will partly compensate for the Sun's loss of mass, making it likely that the Sun will eventually engulf the Earth in around 7.59 billion years. The Sun's atmospheric drag can also cause the Moon's orbit to disintegrate. As the Moon's orbit approaches a distance of 18,470 kilometers, or 11,477 miles, it will cross the Earth's Roche limit, meaning that tidal forces exerted by the Earth will break the Moon apart, transforming it into a system of rings. Most of these orbital rings will begin to decay, and the residual debris will impact the Earth. As a result, even if the Sun doesn't directly engulf the Earth, it's possible that the planet will be left without a moon. But the Earth's decaying trajectory towards the Sun may eliminate the Earth's mantle, leaving only its core. Eventually, the Earth's core would also be destroyed 200 years later. According to this gloomy scenario, the Sun's red giant will simply destroy the Earth, which will evaporate into the hot solar atmosphere and cease to exist. But the story of the Sun as a red giant doesn't end there. As the hydrogen nuclei continue to fuse around the core, more helium will flow into the center, and the temperature will rise even higher. The cycle is fueled. Hydrogen fusion in the shell around the core accelerates, and the helium deluge at the center intensifies. This phase will last 500 million years before the core finally reaches the temperature required for helium fusion, a process that produces carbon and oxygen. This transition from hydrogen to helium fusion is marked by a spectacular eruption, during which the Sun contracts to a more constant subgiant structure. This new equilibrium was short-lived. 100 million years later, in the same way that helium had displaced hydrogen, carbon and oxygen nuclei drove helium out of the core and into neighboring layers. The combustion of oxygen and carbon now requires higher temperatures, at least 600 million degrees Celsius. This time, the core will never reach the temperature required to restart nuclear reactions. Its mass is not high enough to reach the temperatures required to fuse carbon and hydrogen nuclei into heavier, more complex elements. The helium shell continues to burn, and the core continues to contract until Pauli's exclusion principle stops the implosion. This quantum mechanism acts as a repulsion. It's as if the electrons refuse to be compressed any further, bringing the Sun's contraction to an end. The outer layers continue to expand and cool before being scattered across the cosmos. All that remains is a staggeringly dense ball of carbon and oxygen, known as a white dwarf. It will continue to glow for another few billion years. Fusion reactions will cease, and the temperature is no longer high enough. The Sun's thermal energy will be gently dissipated into space, leaving a dark, cold globe. In 9 billion years, the Sun, with a mass equal to 54% of its current mass, will become a white dwarf, composed of carbon and oxygen. Our Sun is now dead, and its core laid bare. Its power of attraction on orbiting bodies such as planets, comets, and asteroids will have weakened due to its loss of mass in the previous stages. All the orbits of the remaining planets will expand. If the Earth is still around, its orbit is now twice as far away as the orbit we know today. All the planets will become dark, icy, and completely devoid of any form of life. They will continue to orbit their star, their speed reduced by the increased distance from the Sun and its reduced gravity. More than 4 billion years later, the white dwarf Sun has cooled to a temperature of 2,000 degrees Celsius, or 3,632 degrees Fahrenheit. Its luminosity falls below that of the Sun. Its luminosity falls below 3 billionths of its current level. Its heat is no longer measurable. It is now invisible to the human eye. So weak is its radiation that it is drowned in that of the cosmic microwave background. The Sun is gradually changing from a white dwarf to a black dwarf. The prospects for the destruction of our planet are not merely speculative, but based on solid predictions based on our scientific advances. Although we have knowledge of the Earth's distant future, it is up to us to shape the short-term future. This perspective raises fundamental questions about the future of life on Earth and our responsibility as a species to be aware of this potential future. It is crucial that we deepen our scientific knowledge, develop environmental preservation strategies, and explore innovative solutions to prepare our planet's biodiversity and sustainability. While this may seem a long way off on a human scale, it remains an inescapable reality in the natural evolution of our solar system. Understanding these phenomena and their implications enables us to better appreciate the importance of preserving our environment and exploring new avenues to ensure a sustainable future for generations to come. This is the ultimate dream of a scientifically literate society, and our only hope of staving off, as far as possible, the imminent threat of human extinction.